Welcome back to Tech 259 on Monday, March 29th. In the previous video, we talked about how current flow through a conductor can cause a magnetic field, will cause a magnetic field, and we can determine the direction of that magnetic field by the right-hand rule for current carrying conductors. At the end of last video, we talked about kind of the opposite, which is to say that a changing magnetic field can induce a voltage in a conductor. So we're going to go into more detail about that in this video. We're going to have another hand rule in this video. And we're going to start by talking about an experiment. So I'm actually going to show you an experiment to start to motivate this idea, which will lead to generators, our discussion of generators. So to show you that experiment, I'm going to switch over to the document camera. What I'm going to start by doing now is a quick experiment. And this was an experiment that Michael Faraday would have done in the early to mid 1800s. So what I'm going to do is, I don't know if I can show you the entirety of the experiment, but what I'm going to show you is a multimeter. And I've got that multimeter here. Let me move the webcam a little bit and I'll show you what we've got. So what I've got is a multimeter, and the leads of this multimeter are connected to the wires of a coil of wire. So this is a coil of wire wrapped around an old water bottle. And I don't know how many turns or loops are in that coil of wire. There's probably somewhere around 50 to 100 turns or loops of wire in that coil. And I've got the output hooked up to the leads of the multimeter. So what I'm doing right now is I'm measuring the voltage of this coil of wire. And of course it's zero. There's no reason why it wouldn't be zero. All right, and what I've also got here, I've got a desktop magnet. So this is actually the base to kind of one of those desktop sculpture type things where you can stack metallic cubes and cylinders on top of it and make kind of creative shapes. You may have seen something like that. But all I really care about for our experiment right now is that this contains a magnet in it. It's not a particularly strong magnet, but it's good enough. So what I'm going to do, let's see if I can, I don't know if I can show all of this at the same time. This is complicated by the fact, I don't know if I've mentioned this before, but the field of view that you see is different than the field of view that I can see on my window. For whatever reason, it's not the exact same field of view. So I'm pretty sure you can see this whole multimeter now, including the numbers. And I want to try and get you to see as much of this as I can. So what I'm going to do is I'm going to play around with this coil of wire in relation to this magnetic field. All right, so I'll move that just a little bit. All right, so what I'm going to do, there's no magic or wizardry here, other than Faraday's law, which I guess in itself is kind of a form of wizardry, I suppose. But all I'm going to do is I'm going to take this magnetic field and I'm going to bring it close to this coil of wire. So I'm slowly going to bring it together, and I want you to watch the multimeter as I do that. All right, so I saw it get up to about 0.3, excuse me, 0.003, 3 millivolts. And let's do it again. Oh, it turned off on me. All right, so I'm going to bring it close together, slowly. Okay, I saw 5 millivolts. I'm not sure if you're seeing the exact same thing because it's going through the webcam, so I don't know how many, images per second the webcam is taking. But I saw 5 millivolts, positive 5 millivolts when I brought them together. Now I'm going to pull them apart slowly, and you notice it's a negative number now. I think I saw negative 4 millivolts that time. So now I'm going to try and do it a little bit faster. I'm going to bring the magnetic field together a little bit faster. And I saw 9 as I was looking directly at the multimeter, not at the screen. I don't know what the screen showed, but I saw 9 millivolts. Now I'm going to pull it apart a little bit faster. I saw negative 14 millivolts that time. Now I'll try to bring it together a little bit faster without damaging or crushing the water bottle. Okay, I saw 17 that time. So we got 17 millivolts measured in the coil of wire. That's an induced voltage in the coil of wire. Now I'm going to pull it apart quickly. I saw negative 17 that time. That worked out fairly consistently. It doesn't always work out quite that consistent. All right, so what we've showed so far is that if we have this movement of the magnetic field close to the coil of wire, then we induce a voltage. I want you to notice right now we have the magnetic field close to the coil of wire, but we're not inducing any voltage, right? So there has to be some movement, evidently, some movement between the magnetic field and the coil of wire in order to induce a voltage. I do have magnetic flux here, right? Because I've got that magnetic field coming from the magnet, and that magnetic field is going through the coil of wire. So it's not just the magnetic flux that creates the magnetic field. What we're going to say in a little bit is actually it's a change of magnetic flux going through the coil of wire that induces the voltage. So it has to be a changing magnetic flux. All right, so I can pull it apart. I saw negative 11 millivolts that time. All right, so one more thing I can show with this. So far, I've been holding the coil of wire stationary. I've been moving the magnetic field relative to that. It doesn't really matter which way I'm moving it. I'm going to induce a voltage as long as I am changing the magnetic flux. I've shown that I can induce a voltage by holding this stationary and moving the magnetic field. Now I can do the opposite and think about what we might get here. So I'm going to hold the magnetic field stationary. I'm going to move the coil of wire. So I'll move it close together. And I saw, I think, 11 millivolts that time, and now apart. I saw negative 15 millivolts once again. I saw 13 millivolts, negative 13 or negative 14 millivolts. So it seems that it doesn't matter which one I'm moving, right? So as long as I have motion, relative motion, we're going to call it relative motion. As long as I have relative motion between the magnetic field and the coil of wire, then I induce a voltage. Notice I can't just say that I have motion, because now I've got motion, right? I'm moving both of them, and I really don't have an induced voltage, right? There might be a few very tiny fluctuations, but there's really no induced voltage here when I'm moving both of them. I have to move one of them relative to the other in order to get an induced voltage. All right. The one more thing that I wish I could show easily, but it's not easy to show. We could also change the amount of induced voltage by changing the number of turns or loops in this coil of wire. So if I added 50 or 100 more loops of wire, what you'd actually see is a larger induced voltage. And as it turns out, the induced voltage is actually directly proportional to the number of turns or loops in this coil of wire. So if I doubled the number of turns in this coil of wire, I would double the amount of induced voltage. All right, so that's what I wanted to show with that experiment. That was an experiment that Michael Faraday would have done in the early 1800s. And we can summarize the important findings here. We can say that, first of all, we can say that, here we'll say Faraday's experiments first of all, they showed that the magnitude of the induced voltage in a conductor, the magnitude, by magnitude I mean absolute value. So I'm not worried right now about whether it was positive or negative. I'm just interested in the magnitude or the absolute value of the induced voltage. So the magnitude of the induced voltage in a conductor is directly proportional to the number of turns of wire in a coil, to the number of turns. Turns is the term that we use most typically. You can also think about just loops. A turn is a loop of wire in that coil. The number of turns of wire in the coil. It's directly proportional to the number of turns of wire in the coil, which means if I double the number of turns of wire in the coil, I double the induced voltage. If I cut the number of turns of wire in half, then I would cut the induced voltage in half. And we can write this mathematically by writing E induced. Now don't ask me why, I don't know why this is, but the term that we use for induced voltage, the variable is E. So you're gonna have to kind of get used to that. Voltage is often abbreviated with the symbol V, and it's also in generator theory, which is what we're leading toward right now. In generator theory, induced voltage is usually symbolized with the letter E. So E induced is proportional to, that's a Greek letter alpha, that means proportional to. It's proportional to N, where N is the number of turns in the coil. The second one is a little bit less intuitive, but I think I can make it a little bit more intuitive by showing you that experiment. So hopefully this makes a little bit more sense than it would have if I had just written this down directly, or if you had just read it in the lab manual, which you should do, by the way. This one also says that the magnitude of induced voltage in a conductor is proportional to I should have said directly. It's directly proportional to this is the complicated phrasing here, but I think it'll start to make sense if you think about it. It's directly proportional to the rate of change. The rate of change. So rate of change means how quickly something is changing. The rate of change of magnetic flux through the conductor. So this is what I was trying to show with the experiment as well. Magnetic flux alone does not do anything for us. We do not induce a voltage in a coil of wire just by having a magnetic flux through that coil of wire. But if I'm changing the magnetic flux, and that means I'm creating relative motion between the coil of wire and the magnetic field, then I have a rate of change of magnetic flux through the conductor. And we saw in the experiment that if you have a rate of change, if you have a changing magnetic flux through the conductor, that's when you're going to induce a voltage. Specifically, if you have a larger rate of change, that means moving them relative to each other faster. If I have a larger rate of change of magnetic flux through the conductor, then I'm going to induce a larger voltage in the conductor. And we can write that mathematically by saying that the induced voltage, E sub IND is what I'm writing here, E sub IND is proportional to the change in magnetic flux per unit time. So this would be in Webers and this would be in seconds typically. So a rate of change of magnetic flux in Webers per second, the change in magnetic flux per unit time. All right, when we're talking about the change of magnetic flux, so we've got the change in magnetic flux. I'm just going to briefly show you how to calculate this, all right, just so we're all on the same page. The rate of change, or the rate of change is the change of magnetic flux divided by the change in time. The change in magnetic flux, delta phi, is equal to phi 2, or the magnetic flux at time 2, minus phi 1, which is the magnetic flux at time 1. We had that magnetic flux is equal to B times A. B is the magnetic field strength, and A is the area of the coil of wire. So we can substitute that in. We can say phi2 is equal to B2 A2, and phi1 is equal to B1 A1. All right, so we're just saying that we've got a magnetic field and we've got a coil of wire and we're moving it from one position to another position. And the change is equal to the magnetic flux at time 2, its final position, minus the magnetic flux at time 1, its initial position. So we can calculate those by taking B2 times A2. That's the average magnetic field strength and the area of the armature at its final position, minus B1A1, which are its average magnetic field strength times its area of the coil in its initial position, position 1. All right. The thing to pick out here, though, is that the shape of the coil is not changing. We're not deforming, we're not bending or deforming the coil of wire as we're moving it around inside the magnetic field. So A2 is the same thing as A1. So we can simplify this, and we can say A2 is equal to A1. So let me just call that A, and I'm going to factor that out. So I can say this term is equal to A times B2 minus B1. So that is a useful relationship. You're going to use that quite a lot. The change in magnetic flux is equal to the area of the armature, or the coil of wire. We'll call it an armature in a little bit. The area of the coil of wire times the magnetic field strength at time 2 minus the magnetic field strength at time 1. Okay. All right, so we had these two principles that Michael Faraday developed, and then he put these two together, these two concepts together, into an equation, and that equation is called Faraday's law of induced voltage. Sometimes I'll just say Faraday's law, and you'll know what I mean. It's that ubiquitous. Faraday's law is a really common equation, and it's extremely important in the field of electrical generation. And what it says, we just put these two concepts together. We say that E induced is equal to, there is a negative sign in there, and it's by convention, and it is important. So make sure you have the negative sign in there. And we'll talk about this in a little bit, but if you follow through this calculation and you get a negative number, that's totally fine. It's totally acceptable to have a negative induced voltage. In fact, if you think about AC voltage, it's going up for a little bit and then down, and then it goes negative for a little bit and then goes up. And we'll talk about the shape of the AC voltage waveform, but basically it's a sinusoid. It's a sine or a cosine curve. And so it spends half of its time in the positive half cycle and half of its time in the negative half cycle. So half of the time, generators are producing a negative voltage. So if you're doing a problem and your answer happens to be a negative voltage, that is totally fine. That is totally acceptable. Just leave it like that. Same thing with negative current. You can get a negative current. It just means the current is flowing the opposite direction from a positive current flow. All right, so putting these together, we have our negative sign, and then we have in the number of turns in the coil, and then we have change in magnetic flux per unit time. So this is a really important equation. This is the equation for electrical generation theory, or maybe not the only one, but it is definitely the most important equation for electrical generation theory. So if you look in your lab manual, it talks about different ways that you can increase the voltage in a generator, right? Because all generators use this basic equation to induce a voltage and create electricity. So if you think about how I want to increase this, let's say hypothetically I wanted to increase the induced voltage in my generator. I want to increase the output voltage in my generator. And let's talk about the magnitude, all right? So that way we don't have to worry about this negative sign. I want to increase the magnitude of the induced voltage, or the output voltage, in my generator. I could do that by increasing in, so I could use a coil of wire in my generator that has more turns in it, more loops. I could also do it by increasing the change of magnetic flux. All right, and I can actually do that in two different ways, right? Because we had our change in magnetic flux is equal to the area of the coil of wire times the difference in the magnetic field as this thing is rotating. All right, so there's actually two different ways I can change the change in magnetic flux. That is by either increasing the area, so just using a larger coil of wire, a physically larger coil of wire, which is going to result in a larger generator. Or, this is not so obvious, but if I increased the strength of the magnetic field in the generator, then I would also increase the difference B2 minus B1. So there's two ways of increasing delta phi: larger area of the coil or a stronger magnetic field inside our generator. And the last one is delta T. Delta T is in the denominator, so if I wanted to make this output larger, then I would need delta T to be smaller, right? If I divide by a smaller number, then my output will be larger. So what that means is the amount of time that it took for my magnetic field to move relative to my coil of wire, or vice versa. So how fast I was moving them. So if I'm moving them fast, the delta T will be small. It won't take very long to move it back and forth. If it's slow, then I have a large delta T, and if I divide by a large number, then my output voltage will be smaller. All right, so that's what delta T means. You would increase the speed of relative motion, which would result in a smaller delta T, which would result in a larger output voltage. All right, so that is the basic equation that we use inside basically all generators that have a rotating component, like a turbine, providing the input to them. So now what we want to do is use this principle, and we want to develop this fundamental generator that is common to essentially all rotating generators, all generators that use something rotating to them. All right, because we want to develop something that can create a sustained output voltage. We could have our coil and our magnetic field and move them like this or around like this, but ultimately it turns out to be a lot easier to develop a generator where we use something rotating. And then we can use that spinning kinetic energy, and we can cause a generator to spin, or part of the generator to spin, and that can give us our relative motion that we were talking about. So first of all, it's worth talking about what are the minimum things that we need for a generator. We call this the minimum requirements. Minimum requirements for what we call generator action or generator principle. When I learned it, it was called generator action, so that's what I'll put. Generator action. So think about the things that we had in our experiment just a few minutes ago. We were essentially making a generator. It wasn't a very efficient one, and it wouldn't have been a great idea to use that for a long time, but we did have a generator. So the first thing that you have to have for a generator, you've got to have a conductor. Usually it'll take the form of a coil of wire, but it could be something as simple as a coat hanger, or it could be, if you have a paper clip or something, anything that can conduct electricity could be your conductor, and you could induce a voltage in it. And if you induce a voltage in it, then you've got generator action. The next thing that we had to have in our experiment a few minutes ago, we had to have a magnetic field. Right, so we had our conductor. I had my conductor on this side, and I have my magnetic field on this side. But remember, I did not induce a voltage if I just held them steady against each other. I had to move one relative to the other. So the third thing that you have to have is relative motion. Relative motion, not just motion, remember, because I showed you that If I move the two of them together, I don't get an induced voltage. So relative motion between the conductor and the field. Conductor and magnetic field. And if we have these three ingredients, it doesn't really matter what the conductor is or what the magnetic field is or how I'm getting the relative motion, but anytime I have these three ingredients, I will induce a voltage in that conductor, and we call that generator action. All right, so the actual physical design of a generator was actually, once again, it was initially developed by Michael Faraday, but then there are a lot of people who had a hand in its development and evolution over the following 100 plus years. Some of the big names are Nikola Tesla. I'm sure you recognize that one. George Westinghouse. I don't know if you've heard of the Westinghouse Company, but it still exists, and they were a really big player in developing this as well. Also, a guy named Charles Brush, who was in Cleveland, Ohio, and he was very instrumental in developing this as well. So the original design, and the original design is still basically what we use with some modifications. The original design used rotating, something rotating, and it had a magnetic field around the outside, and that's still kind of our basic prototypical design. So I'm going to go ahead and draw this. Here is a magnetic field with a north pole. And by the way, we said last time that there is no such thing as a monopole. Everything is a dipole. So I'm not really going to draw it all the time just for simplicity, but you should just recognize that in reality, okay, if I have a north pole right here, then I also must have a south pole over here. Typically, I'm only going to draw the north pole here. Just recognize there's a south pole over here also. Then I have a coil of wire, and for simplicity's sake and for drawing, I'm just going to draw one turn or one loop in that coil of wire. So it looks something like this. And I'm trying to draw it in 3 dimensions, but this is going into the page, okay? So envision this loop of wire going into the page. And then these are my outputs. We'll talk a lot more about how you get the induced voltage out, right? Because this is gonna rotate. I haven't said that yet, but this is gonna rotate. We're gonna call this coil of wire an armature, and this is going to be rotating. This is our input shaft to our generator. It's coming in here and rotating this armature, and that input shaft comes from the output shaft of the turbine. So I have the other part of the magnetic field over here. This is our south pole. And once again, I won't usually draw the accompanying north pole over here, but it's there because we don't have any monopoles. So from here on out, I won't usually draw the dotted part here. I'll just draw the north pole and the south pole and the armature. But you'll know that every magnetic field is actually a dipole. All right, so think about what we have here. If we have motion, let's go ahead and draw some motion in here. So here's my output, electrical output, mechanical input, because this is what's being rotated. This is the input shaft of the generator, and let's say the turbine is spinning it in this direction for now. All right, so this is spinning clockwise. All right, my armature is spinning clockwise. And now think about whether we meet these requirements. Do we have a conductor? Yes, this is a coil of wire. Symbolized with just one turn. I'll usually just draw one turn, but in reality this would have hundreds to sometimes even thousands of turns in this coil. Do we have a magnetic field? Yes, we have from north to south. And do we have relative motion between the conductor and the magnetic field? As long as this is spinning, as long as we're causing this to rotate, the armature to rotate inside the magnetic field, then yes, we definitely have relative motion between the conductor and the magnetic field. the next question is, all right, so I induce a voltage in here, and we could calculate if I gave you, or if we measured these things, if you measured the area of the armature and you measured the magnetic field strength at these different positions as this thing rotates, and if you measured how long it took to rotate and you counted the number of turns, you could use this, Faraday's law, and you could calculate the induced voltage here. But it's not quite so obvious just looking at it like this. What is the polarity of the induced voltage? In other words, is this the positive side and this is the negative side? Or is this the positive side of the output and this the negative side of the output? So I'm actually going to give you two different ways to look at this. The more, let's say, actually the more rigorous way, I'm going to tell you first. We're not actually going to use it very much, but it is something called Lenz's law, and that's actually what is going to determine the polarity of the output voltage. After we write that down, and I'm actually going to show you a video about Lenz's law because it's pretty cool, it's pretty neat and kind of counterintuitive. Once I show you a video about that, then in the second part, I'm going to give you a hand rule, kind of like the right hand rule. We're going to have a right hand rule for generators, and that's how, in practice, we're usually going to decide which side is the positive side and which side is the negative side of the armature as it's inducing a voltage. All right, so first, what we're trying to establish here is what is the polarity of the induced voltage. All right. This next part about Lenz's law is not in your lab manual, so definitely want to pay attention to this part because it's important stuff. It's just didn't make it into the lab manual. So the way we can decide the polarity of the induced voltage is something called Lenz's law. L-E-N-Z apostrophe S, named after a guy named Emil Lenz in the early 1800s. He was kind of a contemporary of Michael Faraday, actually. Lenz's law. It sounds a little bit complicated. It's kind of a lot of words here, but I think it'll make sense, especially after I show you a video. All right, so what it says is the direction of current induced in a conductor, and this is a little bit problematic already because we don't directly induce a current, we induce a voltage. However, this is kind of shorthand. We induce a voltage, and as a result of that induced voltage, we get current to flow if we have a complete circuit. So we're not writing all of that, we're just kind of shortening that to say the direction of current induced in a conductor by a changing magnetic field that changing magnetic field is what's giving us the relative motion. Or I guess more specifically, the relative motion is giving us a changing magnetic field. That's a better way to put it. When we have relative motion in a generator, that relative motion between the conductor and the magnetic field is giving us a changing magnetic field. So the changing magnetic field experienced by this armature is caused by its rotation. It only has a changing magnetic field if it's rotating. If it's not, then it doesn't have a changing magnetic field. So the direction of current induced in a conductor by a changing magnetic field is such that, so we're talking about the direction here, is such that the magnetic field created by the induced current, right? Because as soon as we have current flow, then by the right-hand rule for current carrying conductors, we also create another magnetic field. So we have the original magnetic field, that's this is here and this there. But as soon as we induce a voltage and get current to flow in here, then we have current flowing in there, and therefore we have a magnetic field that's created by that flowing current. So this is talking about that current, that magnetic field that is caused by that flowing current in the conductor, in the armature. Right, so where was I? The direction of current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current, which again is the current created from the induced voltage. All right, so it's kind of shorthand here. The magnetic field created by the induced current opposes the initial or original changing magnetic field. All right, so here's the principle that determines the polarity of the induced voltage in here. It's not so easy to see in the armature, which is why I'm going to give you a thumb rule that makes it a lot easier. But this is a better explanation for why. The direction of the current induced in a conductor by a changing magnetic field, so that's the direction of the induced voltage here that results in a current flow, is such that the magnetic field created by the induced current, so this is the magnetic field created by the current as it flows through the armature, either this way or this way, we don't know yet. The magnetic field created by that current flow is going to oppose the initial or original changing magnetic field. That's this magnetic field going from north to south. All right. There's a pretty cool video and a pretty common experiment. I could show you it myself, but I don't have the equipment on hand right now. So I'm going to show you a video of it, a YouTube video. This is kind of a smug looking guy, honestly, who's got a copper pipe there. You can see that right here. I think you can see my cursor. This is just a copper pipe held stationary. And initially what he's got is a steel ball. It's just a steel ball, no magnetic field. It's not a magnet, it's just a steel ball. And he's going to drop the steel ball through the copper pipe, and you'll see that it's going to drop right through. All right. Next, after that, he's going to take a magnet, a ball that is a spherical magnet, and he's going to drop that through the copper tube. And you'll see that it's going to be pretty different. The effect is going to be pretty different. So here we go. There's no sound with this video. Okay, an iron ball, which is basically what steel is made of. So it dropped right through. I couldn't actually see. I'm going to play that one more time. Okay, I did see it drop through that time. So it dropped through very quickly, as you would expect. Next, he's going to take a spherical magnet of the same size. He's going to drop it through, and it doesn't fall out until now. So it took a lot longer for it to fall through this copper tube. And that's because it is a magnet. So here's the full explanation. This is Lenz's law. So what happens is the falling magnet, as the falling magnet is going through the copper tube, you've got relative motion, you've got a conductor, and you've got a magnetic field. So you induce a current within that copper tube, and the direction of the current creates a magnetic field that opposes the field of that spherical magnet as it's falling down the copper tube. So you got this magnet that's falling down, and it's opposed by a magnetic field that's created by current flowing inside that copper tube. So you've got this resistance between these two magnetic fields that are kind of fighting. And eventually gravity wins. Gravity is going to pull it down, but it's definitely slowed down a lot by that oppositional magnetic field. That is, I think, the prototypical experiment to demonstrate Lenz's law. All right, so I want you to know about Lenz's law, but the way that we usually decide the direction of induced voltage in a generator like this is via something called the right-hand rule for generators. The right-hand rule for generators. We can use it to decide what is the polarity of the voltage induced by the generator. So what you do to apply the right-hand rule for generators, you have to use your right hand, but you don't use the same shape as we had for the right-hand rule for current-carrying conductors. What you do is you make a shape like this. I hope you can see that clear enough, where the important part is that your thumb, your first finger, and your second through fourth fingers are all perpendicular to one another. All right, so my thumb is perpendicular to my first finger, and it's perpendicular to my second through fourth fingers, and they're all perpendicular to one another. All right, and then what we're going to do is we're going to align each one of these things to a different part of the generator. There's even a bit of a mnemonic device that can help you remember which part is which. So the first one that we'll talk about is your thumb. And for your thumb, I want you to remember the M sound, the M sound in thumb, because that is going to tell you the direction of motion. So emphasize that M sound, motion of the conductor. So your thumb needs to be pointing in whatever direction the conductor is moving at that point in time. We'll talk about how to apply this in just a minute. The second thing is your first finger. For this one, emphasize the F sound in first finger, because that is going to tell you the direction of the magnetic field. So emphasize the F in field. And the last part is your second through fourth fingers. I think the mnemonic device is not quite as good with this one, but I try to emphasize the C sound, second through fourth fingers, because that tells you the direction of current that flows as a result of the induced voltage. Direction of current that, we'll just say, results from E induced. Remember, to get current to flow, you actually have to have a complete circuit. So assume that you have a complete circuit, and your second through fourth fingers will tell you the direction of current that flows as a result of that induced voltage. So let's go ahead and apply that real quick. So let's go ahead and draw a generator. Here's my north pole. Here's my coil of wire, which we'll call our armature. Here's my south pole. And we said that the motion of this armature is clockwise. This thing is rotating clockwise. All right, so we need to apply this, the right-hand rule for generators. Our thumb is the first thing that we've got written down, so we may as well apply that first. All right, so what we're going to do is we're going to apply the right-hand rule for generators first to this wire in the armature, and then to double check our results, we'll apply it to this wire in the armature. All right, so all I want you to think about right now is this wire inside the armature, this wire segment inside the armature. So right now, this armature is horizontal, but it's in the process of rotating clockwise. It's rotating around like this, but we've taken a snapshot right now. We've taken a snapshot of it as the armature is horizontal. And I want you to think about which direction this wire segment is moving right now. It's horizontal, but it's rotating clockwise. So the direction of motion right now for this wire segment right here is actually up. It's in the process of moving up. That's going to change, of course, in a split second. It's going to be moving in a different direction. But right now, since it's horizontal and it's in the process of moving clockwise, its motion is kind of like my thumb right here. It's moving directly up right now, moving up. Right? Hopefully that makes sense. Likewise, let's do the other one real quick, because if this one is moving up, then that means that this wire segment over here must be doing the opposite. Now we're talking about like my pinky over here. As it's rotating clockwise, right now my pinky is moving straight down. But right now, at this snapshot in time, this wire segment on the right side of the armature is moving straight down. Okay, so I know that when I apply the right-hand rule for generators, then my thumb, if we're applying it to this wire segment, my thumb is going to be up. And now I have to align my first finger with the direction of the magnetic field. This is where it's important. I said it would come into play soon, and this is where it does, because we need to know the direction of the magnetic field. The magnetic field always goes from north to south. I'll go ahead and draw it in here. I won't always draw the magnetic field in, but here's what it would look like. All right, so where the armature is right now, the magnetic field is going straight from left to right. So my first finger needs to be going from left to right. Sometimes it's hard to like contort your hand into the right position, but you can figure it out. You can always figure it out. All right, so what I need to apply right now is my thumb pointing up because it's going up. The thumb goes up, the first finger goes from left to right, and as a result, the second through fourth fingers are pointing down into the page. All right. So my second through fourth fingers are pointing down into the page, so I can draw that like this. It's going into the page because the way I've drawn this, sometimes it's a little bit confusing because we're trying to draw a three-dimensional generator on a two-dimensional sheet of paper. And so sometimes it can get a little confusing, but we'll do some practice with these and I think you'll figure it out pretty quickly. All right, what I like to do then is apply the right-hand rule to the right side of the armature and double check. It should be consistent. It won't be the same, but it should be consistent. Because if current is going this way on the left side, the current flow should be continuous. They shouldn't both be coming back to meet back here. We should have a complete circuit. We're going to have connection here to the electric grid. So the current should be flowing in a complete circuit like this. All right, so I would expect the current should be coming out of the page on this side of the armature. So let's apply the right-hand rule and see if we're right. If we're not, then something went wrong somewhere. All right, so here's my right hand. My first finger is still going to go left to right, so it's like this. And now my thumb is the motion. My thumb needs to go down. So I need to point my thumb down like this, right? This is kind of hard to contort my finger, my hand. But the thumb is pointing down towards the bottom of the page. My first finger is pointing from left to right, the direction of the magnetic field. And my second through fourth fingers are pointing up towards the camera, towards you. So the direction of the current flow that results from the induced voltage is out of the page, like this. All right, so at this point in time, it's going to change in a little bit, but at this point in time, we know that the current is coming from this side, and then it's going through. I could go ahead and draw in some type of load. We'll talk about what these are in a little bit, but let's just say we have a load. Right here. And like I said, my current flow is continuous, so the current is flowing from this side of the armature through here, around here, this way, through the load, and then back to the armature. By definition, current always flows from positive to negative, so right now, at this point in time, this is my positive side, and this is my negative side of the generator. That is going to make it so that current flows from here, this way through the load, and then back here. But we got that because we know that the current is flowing this way on this side of the armature and this way on that side of the armature. All right, so that was an introduction to the right-hand rule for generators and also Lenz's law, and generators as kind of the prototypical design of the generator. So I'm going to go ahead and stop this video. This is kind of a good place to stop, and I don't want this to get too long. In the next video, which will probably be a little bit shorter, I want to talk about the output of this generator, of this very prototypical generator. I actually want to plot what the output is going to look like. All right, so I'm going to stop this here, and I'll see you in the next video.